Thank you for the introduction. Okay, my name is Hiroshi Unno, and this is a joint work with Takeshi Tsukada. And this work, the goal of this work is to establish a precise connection between software model checking and cyclic-proof search. It has been previously known that model checking problems can be encoded as the satisfiability problems of logical constraints over predicate variables such as constraint home clauses or the validity checking problems of fixed point logic formulas. But this work goes a step further to establish a connection between model checking algorithm and proof search heuristics for a non-standard proof system called a cyclic proof system, where internal states of algorithms are partially constructed proofs with open leaves to be discharged. Okay. And from the viewpoint of software model checking, our aim is to provide a unified account for model checking algorithm in terms of logic. This allows us to understand behaviors of many algorithms from simple declarative principles based on single common structure, that is partially constructed proofs. And to compare, the connection is also useful to compare different algorithms. For example, in the paper, we have established an unexpected connection between a well-studied algorithm called property-directed reachability with an efficient algorithm for solving games over infinite graphs, which has not yet pointed even by the authors of that algorithm. And the connection is also, we accept the connection is also useful to develop new algorithms. In fact, in the paper we have derived a refutationally complete variant of PDR algorithm. And from the viewpoint of cyclic proof search, we can import ideas and techniques of software model checking to cyclic proof search. So in cyclic proof search, it is essential and challenging to find an appropriate cut formula because the cut elimination fails for usual cyclic proof systems. So we expect that we can adapt and apply highly efficient algorithm to find an appropriate cut formula developed in the model checking community to solve cyclic proof to cyclic proof search, which has been applied to various verification problems where usual model checking techniques cannot be applied directly, such as entailment checking in separation logic, relational verification, temporal verification, and program synthesis, and so on. In previous work on cyclic proof search, they use rather naive, straightforward heuristics that corresponds to bounded model checking with simple covering. So we want to apply more sophisticated heuristics to such for cyclic proof search. Okay. And okay, in the rest of the talk, I'm going to briefly review backgrounds of software model checking proof systems for inductive systems, and then we explain a key observation to establish the connection between them. And finally, I will use some examples to explain how to interpret various model checking algorithms as heuristics for cyclic proof search. Software model checking is an algorithmic analysis of programs to prove properties of their executions. So let us focus in this talk on safety verification of a while program, where the input is a set of states, D, and initial states, which is a subset of D, and but states and transitional relation on D. Usually, the set of states is infinite. For example, we often adapt D as the set of n tuples of integers. And in the literature, we often use a finite control state, but for simplicity, we omit such finite control state in this talk. And the output is whether a bad state is unreachable from initial state via the transitional relation T. So the property is illustrated here, which says that there is no sequence of states starting from initial state I to B. Model shocking program is to prove this property. And inductive invariant is an essential notion in software model checking, which works as a witness of the safety of a given program, and is defined like this. A subset P of D is called an inductive invariant if all initial states satisfy P, and P contains no bad state, and P is closed under the transition relation. This is an example system where the initial state is a singleton set of 0, and the bad state is a single set of -3, and transition relation is this one. And here we show two inductive examples of two inductive invariants. P1 represents a set of consisting of 2n, where n is greater than or equals to 0, which is an inductive invariant, and it also coincides with the set of reachable states from I. And we also have a P2. This is also an inductive invariant, which contains states which are not reachable from the initial state. But this is also an inductive invariant. And we can show that if an inductive invariant P exists, the system never reaches to a bad state. So the model checkers search for inductive invariants in a variety of clever ways. Okay? And please note that it is relatively easy to check if a given candidate P is indeed an inductive invariant by using an off-the-shelf SMT solver. And let me formalize our model checking problem using the notion of reachable states. The set of reachable states is defined as the least solution mu r for predicate variable P in this logical equivalence. Here, note that defining a property as the least solution of an equation is called inductive definition. And the equation says that initial state is reachable, and any state y, which is one step reachable to x, is also a it says that initial state is a reachable state, and so if there is a state y which is reachable from the initial state, then one step reachable state x from y is also a reachable state. Okay, and so for the previous example, the set of reachable states is defined inductively from the initial state, and state reachable from the one, and like this, and which the set corresponds to this one. Okay, and so proof systems for inductive definition can be used to prove the goal sequence like this. So so model checking problem can be formalized like this, and the system never reaches a bad state if only if this goal sequence is valid. So the goal of model checking is to prove this one. And there exist various proof systems for inductive definitions to prove sequence like this. Let me briefly review existing proof system for inductive definitions. A classical proof rule for inductive definition is due to Martin-Lev. This is the rule presented by Martin-Lev, and the premises requires that phi x is inductive invariant. The first premise requires that initial states satisfy phi, and it also requires that phi is closed under the transition relation T. And the second premise requires that phi has inductive invariant has no bad state. Okay. And however, this rule cannot be used to describe processes of searching for inductive invariance. It is because this rule is applicable only after an inductive invariant phi is found. Okay. So instead of this rule, we adapt a non-standard proof system called cyclic proof system, which is a proof system in which proofs may have cycles like this. And a cycle intuitively represents a use of inductive hypothesis. So we can make a link from open leaf node to some ancestor with the same label. And for soundness, we also need to check a global condition, so-called the global trace condition, which intuitively says that requires that for any infinite path in the graph, the rule for expanding the inductive definition should be applied infinitely often for soundness reason. So, and the rule for inductive definition in the cyclic-proof system just expand the definition, which is applicable without knowing an inductive invariant. So we can use this for describing proof search. So please note that the goal sequence is rewritten to the sub-goal using this rule by expanding the left-hand side inductive definition like this. And let me next explain our key observation to establish a precise connection between model checking and proof search. So we have formalized model checking problem using this goal sequence, which says all reachable states are not bad. However, we found that this is not inappropriate for establishing a connection between cyclic-proof search and ordinary software model checking algorithm, because ordinary software model checkings are based on forward reachability checking, while so this formalization corresponds to backward reachability checking. So we instead use a dual formalization of this. We use this goal sequence, which says that all initial states are safe. And here, a new S characterizes the set of safe states, which is defined co-inductively as a greatest solution of this equivalence, which says that a safe state must not contain a bad state, and also for any state y reachable, one step reachable from x, y must be safe. So the set of safe states is defined inductively like this, and we can formalize model checking problem as the problem of proving this goal sequence. Okay, and we use this one to establish our connection between software model checking algorithm and proof search heuristics. So we perform goal-oriented proof search, a bottom-up proof search, where an intermediate state is a proof with unproved leaves to be discharged. So we deal with open proof tree. And we start from the tree consisting only of the goal secant of this form. And we choose an unproved leaf and select an appropriate proof rule for it. We will later explain various proof rules and heuristics for proving goal secant. But so we have also a rule to expand the definition of the co-inductive definition like this. So given this goal, we can rewrite this goal to this sub-goal by expanding the right-hand side definition of co-inductive predicate to obtain this one. And we then iterate this process until there are no unproved leaves to close the proof, to complete the proof. So let me first introduce our first heuristic, which corresponds to symbolic execution in software model checking, which says we need to try to fit the shape of unproved sequence into this normal form. Okay. For example, so by expanding the definition of co-inductive predicate, we obtain this one. So the open secant is not in the normal form, so we apply rules for the rules of the secant calculus to normalize this one into this form. So by applying some rule, we obtain these two goals. And please note that this one, the left-hand side sub-goal can be discharged by using an off-the-shelf SMT solver because it doesn't contain a co-inductive predicate. And the second sub-goal can be further rewritten into this form and this form, which are equivalent transformation. And we finally obtain this one. And please note that here, this one, from this goal, we obtain this sub-goal. And this corresponds to one-step transition, one-step symbolic execution. So, and also here, this sub-goal requires that initial states are not bad. And this sub-goal requires that next states of I are safe. By generalizing the I with arbitrary formula, we obtain this derived rule for symbolic execution. We call this rule symbolic execution and SE for short. Okay, and we next explain famous bounded model checking algorithm, which is k repeated iterations of SE rule. So starting from the goal, we obtain these sub-goals by symbolic executing from state 1, I, we obtain phi 1, phi 2, phi k, and phi k plus 1. And if one of phi I do not imply negation of B, then we obtain a counterexample within a case step against the safety. Please also note that here there is a open secant. To complete the proof, there's a heuristic called a forward criterion in the literature, which says that here we need to make cycle to close the to complete the proof. Okay, to prove this one. Here, for example, if phi k plus 1 is equivalent to phi, for example, phi 2, then we can make a link from here to this one because the labels are the same. And now this proof is completed. In general, we can regard these sub-goals as induction hypotheses. And in general, we can check this more general condition here. Phi k plus y needs to imply one of phi I. Okay? And this can be discharged by an SMT solver. Also, we can here apply the cut rule to replace phi k plus 1 with this one, the weaker one, to continue the proof search. And note that this one can be further rewritten to these subgoals, where we have phi k, blah, 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 and phi 1 in the left-hand side, which can be closed by making links, backlinks, like this. This is the so-called forward criterion studied in the bounded model checking community. Okay. So we have used a cut formula, introduced a cut formula to to complete the proof. We can have many other options for cut formulas. So we introduce a new rule that combines SE with cut, like this. And for the previous example, we used this disjunction as a cut formula, but we can use instead a different cut formula. For example, let us consider a xi consisting of formulas, predicates, closed under some certain logical operations such as conjunction. Then our second heuristics, let the cut formula be the strongest psi in xi such that this holds, which corresponds to predicate abstraction were studied in the literature. Right? And let me explain the next heuristics, which is also a famous, were used algorithm impact lazy abstract predicate abstraction with interference. We think this algorithm is based on these two heuristics, additional heuristics. The heuristics 3 says we tentatively choose true as the cut formula without being afraid of proof failure. And the heuristics 4 is for refinement. When the proof attempt fails, then we strengthen the cut formula as follows. Replace cut formulas in the partial proof 3 with this one by introducing a new predicate variables qi and solve the constraints on qi. For example, from this one, we apply SC plus cut rule, and we adapt here true as the cut formula. But this one immediately fails because by expanding this one, we need to prove this one. Top implies not negation of B, which doesn't hold usually. Then we refine the cut formulas by strengthening the cut formula with new predicate variables like this, Q1, introducing Q1, and solve a system of the system constraints like this. And actually, a solution of this constraint set is called a Craig interpolation. So in the literature, they have been developed various efficient interpolating theorem provers, which can be used here to obtain interpolants. And by replacing the predicate variables in the proof tree with the interplants, we obtain partial proof tree and continue proof search from the leaf node. Okay. Also, we have established, we have introduced a new heuristics for property-directed reachability, which is also a mainstream software monitoring algorithm studied in the literature. It says that in strengthening, we need to keep as many cut formulas as unchanged as possible. Based on this simple principle, declarative principle, in the paper we have reconstructed PDR-like algorithm. Furthermore, we have derived a levitationally complete variant of PDR using model-based projection based on this principle. And in the paper, we have also established an unexpected connection between heuristics 5 and an existing efficient game-solving algorithm. Right. Okay, let me conclude the talk. So this is the main takeaway message. Software model checking algorithm can be seen as cyclic-proof search strategies. So we have established a connection based on this goal secant, and initial states are safe using this one. Okay, thank you for your attention.
Thanks for the talk.
Maybe you better use this.
So maybe use that, yeah?
Yeah.
Hi, thanks for the talk. I think the main takeaway is very meaningful that model tracking algorithms sometimes just mimic this cyclic proof. But in practice, I think model tracking, what they use is much easier because when they cut, they try to prove it is based on a set of states, the set of numbers of the states. But when we check this reoccurrence to cut the proof to prove it, we need to prove a formula of reoccurrence, which is not that simple to be done in practice because there are sometimes incompleteness there. Do you have remark on that?
So you mean it is not in practice easy to apply such software model checking techniques to general cyclic proof search?
Yes.
Yeah, it's correct. Yeah, it's because yeah. So yeah, you are right. I agree with you. And software model checking algorithm usually only designed for restricted shape goals sequence like this one. That's why in general cyclic proof search, we cannot directly apply software model checking algorithm heuristics. Yeah, I agree with you. But actually, there are, for example, in cyclic proof search, sometimes subgoals of these shapes occur in general cyclic search. In that case, we can directly apply software model checking techniques to discharge goal sequence like this. And so our ongoing work is to extend the generalized software model checking techniques to more general goal sequence, which is non-trivial, as we pointed out. Yeah, yeah, it's ongoing. I have no answer. Answer now, but yeah.
Any more questions? I have a quick question. Maybe it is related to the previous one. Can you just elaborate a little bit on what you mean by reputationally complete variant
Okay.
IC3 PDR?
Okay. So if the target program has has an error path starting from initial state to error state. Refutation completeness guarantee that our algorithm can always find some.
Can you elaborate on the completeness? Why is it complete?
Why it is complete?
Is it because of predicate abstraction or something?
Yeah. So our new algorithm is reputationally complete because we use so the source of divergence was in the previous visual algorithm that possible counterexample obtained from the program can be infinite, while we use model-based projection technique to classify the set of counterexample into finite sets. That's why, and we eventually find it, or we eventually animate all the finite partitions to guarantee the termination. But it's a bit technical, so then we can talk about
But it is complete. I mean, that you do get everything into that finite partition.
Yeah.
Any further questions? Okay, let's thank the speaker.